Okay, so what we've been able to do today so far is we've been able to, from this, we've really figured out that if we make h small enough, then we can sort of start to see a trend as to what the instantaneous rate of change should be. Okay, so we can see it's 1.9, you get 1.909, and we can sort of tell, the more 0.00001, the more 9s you're going to add. And we've just had a little lively discussion about the merits of this, where 0.9 recurring is equal to 1. So what do we have to make h equal to, do we think, to find the instantaneous rate of change? Well, can we do that though? Because remember, we were using this formula here. So the instantaneous rate of change is approximately equal to f of, I'm going to start using x plus h. So x being, we wanted to know at 1. I'll use an a actually, because x is a variable. So a plus f of a over h. So what would happen if we made h 0? We'd have to divide by 0, and we can't do that, no matter how much we want to. Okay? So we have this interesting situation here. I want to know what this is with h being very, very small, but it can't be equal to 0. What I can do with this then is I can say, okay, well, what is the limit going to be as h approaches 0? So the way I write that is I'm going to say the instantaneous rate of change is equal to the limit as h approaches 0. So h is not equal to 0, but h will approach 0 of f of a plus h plus f of a over h. So what we're saying is that on a function f of x, on some function, so this is f of x, at some point a, we have f of a, okay, and we want to know the instantaneous rate of change, so the gradient of that tangent line is going to be by this formula here, as h approaches 0. Now this thing is a new thing that you haven't seen before, or at least we haven't done in class. Have you seen it in Math C? Probably not, no? So let's have a look at how we can work with this. So let's do the same question we did before. So I want to know the instantaneous rate of change at x equals 1 of f of x is equal to 4x take x squared. Okay, so now I need f of a, so f of a will just be, no, a is 1, so that'll just be 1 is equal to 4 times 1 take 1 squared, which is 3. F of 1 plus h will be 4 by 1 plus h take 1 plus h squared. Okay, and I can actually expand this a little bit, so I have 4 take 4h take 1 plus, so this is 1 plus 2h plus h squared. So that's 4 take 1, which is 3. Negative 4h take 2h is negative 6h. And then we've got negative h squared. Okay, so this is f of 1 plus h and f of 1, which is 3. So our instantaneous rate of change, I need some shorter way of writing that, is going to be the limit as h approaches 0 of, so we've got f of 1 plus h minus f of 1 over h. Now, the way I evaluate limits is now at the moment, if I were to make that h equal to 0, I would get this value would be infinite. Okay, so at the moment I can't make that h equal 0, so I'm going to hold that there until I see something that I can do with it. So you'll see what I mean in a moment. So I've got f of 1 plus h, so I've got the limit as h approaches 0 of 3 take 6h take h squared, take away f of 1, which is 3, over h. Now, these 3's are going to cancel out. So I have the limit as h approaches 0 of negative 6h take h squared on h. Now who can see what I can do with this? I could factorize it, and why would that help me? I'll get rid of the h on the bottom. So I'll factorize it, just come across to do that, and I get I get h outside of negative 6 take h over h. These h's will cancel, and I'm left with the limit. I've done something wrong somewhere. This should be a plus up here. Means that this is a 2. Okay, so I've got the limit as h approaches 0 of, that's a plus as well, 2 take h. So what does, guys, if I make this h 0, what do I have here? If I make this h equals 0, what do I have? 2, right? As h approaches 0, so, 2 take h, we were seeing that before. 2 take 1 h, 2 take 1 is 1. 2 take 0.5 is 1.5. 2 take 0.1 is 1.9. 2 take that is that. Okay, so I end up with, if I make h0 here, that's equal to 2. So these, in a way, they cancel out. I've evaluated that limit, and I get the instantaneous rate of change at x equals 1 is 2. And that's exactly what I saw before, except I've done this in a little bit more mathematically robust way, I suppose. All right.